Welcome everyone. For today's prep, we're going to see how to computationally find the intervals of concavity. And we've seen how to do this graphically. Given the graph of a function, we kind of identify the shapes on the graph. But now we're going to see how to find those intervals using the second derivative. And the main result that we're going to use is kind of describes how the concavity is related to our second derivative. So if we're looking at an interval from a to b, if our second derivative is greater than 0, so if our second derivative is positive on that interval, then the original function f is concave up on that interval. And if the second derivative is less than 0, so the second derivative is negative, well then the original function f is concave down on that interval. So the main result here, we can kind of summarize, is that if our second derivative is positive, well, then we can say the original function f is concave up, abbreviate that CU. And then if our second derivative is negative, well, then our original function f is concave down on that interval. And so we want to know where f double prime is positive or negative. Well, what we're going to do is we want to look for where f double prime switches signs. And that can happen one of two places. It can happen when f double prime is equal to 0, or it can happen if f double prime does not exist. So we're going to be looking for where f double prime is positive or negative, and these places where the second derivative is either 0 or does not exist, we're going to call these possible inflection numbers of the original function f, because it turns out that these are going to be the places where our function might have an inflection point. If it does have an inflection point, it's going to happen at one of these two places. And so why we're going to be interested in these? Well, one, it's where we might actually change concavity, but in the context of the second derivative, if we're interested in knowing where the second derivative is positive or negative, these possible inflection numbers, these are the possible locations where f double prime switches signs. So the only way a function can go from positive to negative is if it either crosses the x-axis, it actually goes through the x-axis, intersects it, or it jumps across the x-axis. So that's what this does not exist. We could have like a jump. All right, so we're going to be looking for these two places, and this should feel pretty similar to what we did for intervals of increase-decrease. So our strategy here is going to be, if we want to find the intervals of concavity, the first step is to calculate the second derivative, and usually try to factor it right away. And then once we have that second derivative, we want to figure out where it's equal to 0, and this is a typo. It should be second derivative, where the second derivative is undefined. And then we're going to do a sign chart for f double prime. So this is very similar to the process that we did for intervals of increase-decrease. Except now we're doing it for the second derivative. So this process here, we kind of get, it's kind of nice. We get to reuse our strategy that we did for f prime and finding the intervals of increase-decrease for function f. But now we're going to be looking at the second derivative and finding the intervals of concave up, concave down. So let's save example 1. I'll save that one for class. Let's jump down to example 2. Let's find the intervals of concavity for this function. So the function here is 1/3 x cubed minus 2x squared plus 3x plus 1. And we're going to find the intervals of concavity. We'll come back and talk about the inflection points in a second. But let's go through and find the intervals of concavity. So the first step is we got to get our second derivative. So, well, to get our second derivative, that means we need our first derivative. So let's calculate f prime. So if we differentiate the first term, we get x squared. Differentiate the next term, we get minus 4x. And then finally, plus 3. So that's our first derivative. All right, so let's get our second derivative now. So we just keep differentiating. So differentiate the first term, we get 2x. Then differentiate that minus 4x, we get minus 4. And that's our second derivative. And if there were some higher powers of x, we'd want to try to factor this. But this is already a linear term, so we don't really need to factor it any further. All right, so we've got our second derivative. It's pretty much already factored for us. So now what we want to do is we want to look for these possible inflection numbers. These are the places, ultimately, where our function might have an inflection point. And just like with first derivative, we called these the possible critical numbers. This is where the second derivative is either 0 or where the second derivative does not exist. All right, so let's start with in this case, the easier of the two, and that is where does the second derivative ever not exist? And so usually this happens if we have division by 0. If we look at our derivative, though, the second derivative there, if there's no division by 0, there's no negative exponents, no fractions, things like that. So in this case, none. We will see examples where that happens, but in this case, there's no place here where the second derivative does not exist. So instead, we're just going to take our second derivative, set it equal to 0, and then we'll solve that for x. And if we just directly solve this, add 4 to both sides, and then divide both sides by 2. So when we do this, we get x equal to 2, 4 over 2. All right, so this is our possible inflection number. If the original function does have an inflection point, it's got to happen at this place. All right, so now we use this number, though, to do our sign chart for f double prime. So let's try it out. So we're going to do our sign chart for our second derivative. So let's draw our x-axis. And we're going from minus infinity to plus infinity, and we've only got one possible inflection number, so let's put that right in the middle. And what that does is it splits up our x-axis into 2 pieces, 2 intervals. Okay. And in this case, we only have the one factor, so there's not too much we would need to include on our sign chart. But we do want to have our row for f double prime. And then that'll tell us what f is doing. And if we want, it doesn't hurt to use some test numbers here. It's moving around on me. All right, so just like we would do for intervals of increase, decrease. So let's pick some test numbers here. And, we want to pick a number that's less than 2. So 0 is always a nice one to use. So let's take the test number 0. And when we do this, well, let's write down our lone factor here, 2x minus 4. And we're just going to take this test number and we're going to plug it in. And we end up with 2 times 0 minus 4. So we end up with 0 minus 4, that's a negative. So we end up with a negative result here. And so what our main theorem here tells us is that when the second derivative is negative, the original function has a concave down shape. Okay, well, let's go to the next interval. So pick a number bigger than 2. So, keep it easy, maybe like 3. Plug it in. So we end up with 2 times 3 minus 4. We don't really care about the number. We just want to know, is it positive or negative? Well, this is 2 times 3 is 6. So we're going to end up with 6 minus 4, positive 2. So the main result here is that this is positive, which tells us then that the original function is concave up on that interval. Okay, so what we found is, let's write down our intervals then. Let's actually answer that part of the question. So we found that f is concave up on the interval 2 to infinity, and f is concave down on the interval minus infinity to 2. Okay, so we got our intervals. What else was the problem asking for? One of the inflection points. So in step 2 here, when we figure out where the second derivative is either 0 or undefined, we call those the possible inflection numbers. So for this x value to actually correspond to an inflection point, there's a little bit more we need. So for it to be considered just an outright inflection number, well, it's this number x equals c. We either need the second derivative to be 0 or undefined there. And what we need, there's 2 additional things. One, it has to be in the domain of the original function. And f double prime has to switch signs there. So there's kind of 2 additional things that we need to look for. Is it actually in the domain of our function? And do we have a sign change on our sign chart? So if we wanted to find the inflection points for a function, we would go through and find the intervals of concavity. And then once we have our possible inflection numbers, we just want to go back and look for these 2 extra conditions. We want to check if it's in the domain, and then check to see if we have a sign change. Or another way to think of that, check to see if you have a change in concavity. And then if we're interested in the point, we would find the y-coordinate as well. So right now we've only found the x-coordinate. All right, so let's go back and check these things out. So we found our possible inflection number. So that's where one of those 2 conditions happen. Well, let's look at this x equals 2. And we want to know 2 things. Is this number actually in the domain of the original function? That's the first thing. Is this in the domain of f? And if we go back to our original function here, yeah, we can take x equals 2, plug it in, and we don't get any division by 0 or anything like that. This is a polynomial, so its domain is all real numbers. So in this case, check. X equals 2 is in the domain. Well, what's the other thing that we need? Do we have a change in concavity? And this, we have to go to our sign chart. So let's look at x equals 2 along our sign chart here. And if we look, we do see a sign change. F double prime goes from negative to positive. Or another way to think of that, we go from concave down on one side to concave up on the other side. So, yeah, check. There is a change in concavity there. So we wouldn't be able to figure this part out until we actually do this sign chart. So we wouldn't know right away if this definitely is going to be an inflection point. So x equals 2 actually is an inflection number. So now we know x equals 2, we do have an inflection point there. And so the last part of this is to figure out the y-coordinate. So for an inflection point, the word is point, we want an x-coordinate and a y-coordinate. And the way we find our y-coordinate is we take our x-coordinate and we plug it into the original function to get the y-coordinate. Whoops. And when we do that, we get our y-coordinate is whatever f of 2 is. And in this case, if we plug in, we get 8 over 3 minus 8 plus 6, so minus 2, plus 1. So what is that? Negative 8 plus 6, that's negative 2, plus 1, negative 1, and then we have 8/3. So this ends up being 5 over 3. So our inflection point then, if we put it all together, is x coordinate is 2 and y coordinate is 5/3. So we've got our intervals of concavity and we found our inflection point. All right. So we'll try a few more of these in class and we'll kind of spice it up a little bit. So we'll see you then. Bye-bye.